Assalamu alaikum.
وعليكم السلام ورحمة الله وبركاته.
Okay, so we start now. You guys have any question about any concept here? I told you about different concept in thermodynamics. So if you have any question from the last lecture, basically it was a review of 202. Most of the topic you already know. So I hope you will not have any difficulty. So we have here, we talk about dimension, units, force we talk about, okay. Temperature we talk about this one, absolute temperature. We talk about pressure, okay. This should be P, this should not be F, this should be P. We talk about pressure measurement, absolute
It
internal
should be
pressure,
V,
you already
right?
know.
It should be V.
Yeah. What?
You said now it should be V.
P, pressure, P. Pressure, P, this one.
B.
It
Okay.
should be P. This is also should be P. This is P is equal to rho GH. That's by mistake I write. Okay. And we talk about, you have any question now, let me know. If you do not have any question about work, about pressure, about temperature, and about the derivation, this is, as I told you, that the force is work is equal to force into distance. A small work by sigma W. A small work. Why small work? Because we want to integrate. So we take a small work. And force is pressure into area. Because this is very important how we derive. Because you see this formula very often. So you should know how we derive the formula here. So this area is constant. So area go inside the derivative. P dAl. So this area into length is the volume, right? Meter square into meter. So that becomes meter cube. So this is a volume. This is pressure. So when we integrate, this goes away. Total work, this is small work, and this is total work. You see the difference? There is no sigma here, and there is no d here, because this is total work, not small work. Basically, integral sign, as you can see, this sign is sum, S. Integration is nothing but the summation of the quantity. So that's why this called is S, this integral sign. This is S. Okay, so remember this. W is P delta V, or if pressure is not constant, you write this way. If the pressure is constant, you write this way, P delta V, simple. P comes out. But if process is not constant pressure, then P is inside the integral. So there are two ways you can write it down. So remember this. Okay. So when we talk about pressure also, I told you that work is nothing but area under the curve. If you plot pressure versus volume, you have this curve. So area under the curve is called the work. Also you should know this. Then we talk about heat. Then we talk about different forms of energy. Right? We talk about different forms of energy. Then we talk about open and closed systems. This is open system. As I told you, work and heat, these are the forms of energy that goes into the system and comes out. But they are not stored as W or Q. They are converted to these forms, internal forms. These are internal forms of energy, internal, inside the system. When these forms comes out, they only come out as work or heat. and if they go in and goes in, they work or they go in only as work in heat. Remember this. This is the most important difference. Okay, so you should know this one. When we talk about closed and open system, you already know this, I believe. Energy and mass transfer. Uh, we have here energy transfer for closed system, yes, but mass transfer, no. Open system, yes, both are transfer. Isolated system, no transfer. Yeah. And I give you example, practical examples for closed system and open systems. Mostly we in the refinery we have mostly open systems. Then we talk about extensive and intensive properties. Okay, this I already told you before. Then we talk about the state. State is a condition of the system at any given time. Like at 9 a.m., I go and take the photo, screenshot, and I note the pressure, temperature. This is one state. Then I take again the photo. There is some difference. I say it has undergone a process. Something has happened to the system. Okay, so this is called a process. If they are both same, I will say there is no process. If both here the condition is same as here, I will say system has no process. Okay. So now we have, then I told you isobaric, isochoric, isothermal. I know you guys know it from 202 already. Then I told you that UHTP, they depend on the state. They don't depend on the path. They depend on the state. State 1 and state 2. If I go here, like I have internal energy 100 kilojoule in this state. I go here and I come back here again, U will be 100. Okay, there will be no change value in U. If I have a cyclic process, in a cyclic process, the U will not change here. It may be different here, like I go from U 100 kilojoule, I reach here maybe 70 kilojoule. When I go back, it become again 100 kilojoules. U, that is why I say this is state function. U, enthalpy, temperature, pressure, they are state. They depend on the state, not on the path. Whereas work and heat, they depend on the path. And I showed you here, if you go from Jammu to Makkah, there are two ways you can go. Either you can go from Jeddah and then Jeddah to Makkah, or you can go from Hules. Before going to Jeddah, you take the exit of Hules, and from Hules you go there. So there are two paths here. One is this path, and one is this path. So the work done by the car will be different, depend on the path, right? Here. So work depend on the process. So isothermal work is not equal to isobaric work. Remember this. Then we talk about equilibrium. Now what is equilibrium is? Steady state, you already know. Steady state, no variation with time. In equilibrium, no variation with time plus no variation with position. So if I have everywhere temperature equal, I will call it thermal equilibrium with position and with time. Okay, like this. Then we talk about reversible process. Here we have a process that can be reversed in both direction. It's called a reversible process. That is when I go from this state and I come here and then I go back, I must have the same condition. Then the process is reversible. Otherwise, it is an irreversible process. Okay? Put this in mind. And this is an ideal case. It never happens in the real life. It will never happen, but it tells us about the maximum efficiency of any process. How much is the maximum efficiency of a given process would be under ideal condition. Okay. So here in thermodynamic, we say process reversible to make our calculations is frictionless. Okay, there should be no friction, and it should be only very small from equilibrium disturbance, very small, as I told you here. If I go up, like 25 to 25.00001 degrees centigrade. If I go back from this, maybe the process reversible. I will reach 25. But if I go from 25 to 26, 27 degree, the process may not be reversible. Okay. So this I told you. Now you have any question?
Nope, clear.
Very good. Now we talk about the first law of thermodynamics. This is a statement. Energy cannot be created or destroyed during a process. It only changes the forms. For example, consider closed system. This system is closed, okay, because there is no mass transfer, there is no leakage, there is no pipeline. It's a closed system. Now we supply heat. When we supply heat, this piston can move. So the gas will expand and it will move up. When it moves up, it does some work on the surrounding, right? This is my system. Okay. So this is the energy in, this is energy out, and there is the energy inside. Okay. So when I write the first law of thermodynamics, I write in the form of equation energy in minus energy out plus any energy generated because of a heating coil. If I have a coil here inside this cylinder, if a heating coil, the coil will generate energy, but in this case I have no heating coil. So energy generated will be zero. Okay. Change in the energy of the system, delta E. Okay. So what is energy in our case here? In our case here, U in, right? U in. So this is positive, as I told you. Um, Energy in, we supply the heat and it is positive because heat is given to the system, and energy out, that is work, because this is work done by the system according to our sign. Okay, energy generated is zero because there is no reaction here, because if the reaction is exothermic reaction, you will have heat generated. So no reaction here, and there is no heating coil, no heating coil like this, so we have no energy generation, and that is why this sum is zero. Okay, so we write energy in minus energy out equal to the change in the energy of the system. Okay, this is, now this energy of the system is the sum of kinetic energy plus potential energy and plus the internal energy. Okay, because the system is not moving, the cylinder is not moving, it is there already. Okay, therefore this, because the velocity is zero, kinetic energy is half v square. Because the velocity is zero, kinetic energy change is almost zero. Similarly, the potential energy is zero. Okay, so this term is zero. Oh, sorry, this term, these two terms are zero. So we have only this. So I write Q minus W, they are same here, whereas this delta is come here, U, and it is a function of temperature. UT is a function of temperature. It is not multiplied by the term T. Okay, there is no multiplication here. When we write in the bracket, we means that U depends on temperature. Okay, remember this. So we call this first law of thermodynamics for the closed system. Okay. Now, if I divide this throughout by the time, like Q over time, W over time, delta U over time, what I will get? I will get the rate per unit time. So whenever in your book you see a dot, it means that this is the rate of energy in per unit time. This is only kilojoule here. Here you have only kilojoule. Here you have only kilojoule. Here you have only kilojoule. But when you divide by time, you will see a dot, means the rate per unit time. So now it will become kilojoule per unit per second, or whatever unit you are using for time, kilojoule per hour or per second, and this is also kilojoule per second for that time period, 5 seconds, 8, 9 seconds, whatever. Okay, this is the way you write when you have a rate in. Or we can write, if we are right in this format again, we can write as I showed you just now that W can be replaced by the integral V1 V2 PdV, okay, is equal to delta U. You know already this derivation I showed you above. You can go back and look at it. So this is the form for the closed system. Now, if the pressure is constant for an isobaric process, what will happen in this isobaric process? The pressure P, this will come outside the integral because this is constant. If you know from mathematics, anything that is constant comes out of the integral. So I can put this P out because I have constant pressure here. This one, this constant pressure. Okay. So I can take the P out of the integral, and therefore I can do the integration. So what will I have? This delta U, this is delta U, this will go on the other side, and this is P delta V, P delta V, right? So P delta V plus delta U, we know from the definition of enthalpy, H is equal to U plus PV. So delta H is P delta V plus delta U. So we can replace this P delta V plus delta U by delta H. So for closed system isobaric process, this is the formula. Remember, this is the formula for isobaric process, the heat delta H. Now again go back to the top and suppose that we have a isochloric process, constant volume process. In the constant volume process, delta V will be 0 because the volume does not change, the piston does not expand, so this is 0. So when I say P into delta V0 is 0, so PQ is equal to delta U. So for isobaric process is Q delta H, whereas for isochloric process this is equal to Q is equal to delta U. Now you can see that Q depend on the process. See, isobaric process we have delta H, whereas for constant volume process we have delta U. Remember this, see, the Q depend on the process, but not on this one, delta U. Okay. Now, this is all about closed system. This all we see, this is for closed system, where we cannot have any mass transfer. For example, in the storage tanks, you put some oil and you leave it there, it becomes a closed system. Only heat can transfer. Now we talk about open system. Now open system, you can see that mass is coming in and mass is leaving. Now here the condition is different. Okay. So now here point 1, this is my point 1, this is called the entry point, and this point 2 is called the exit point. In the closed system, we do not have entry or exit point. See here. In the closed system, if you look at the diagram, there are no entry because it is closed, right? So therefore, we have here we have entry points because this is open system. So this point number 1, and I will say the energy in the gas here as the sum of kinetic energy plus potential energy plus internal energy at point number 1. Okay. At point number 2, I will have energy, okay, for kinetic energy plus potential energy plus internal energy, point number 2. Now I will apply first law of thermodynamics. This is like your account, your hisabakum in the bank, where you put, like, for example, you have 5,000 real in your account. Now you put 2,000 real and you take out 1,000 real, right? So you put 2,000 real, so the account becomes 7,000 real, and you take out 1,000 real, so account will become 6,000 real. The same thing happening here. consider this is your bank account. You put some money there and you take out some money there. Okay. So this is very and some money maybe the bank give you some profit. So that is the profit generated here. Okay. It's like energy generated, like the money generated, because bank give you some profit if you want to ask them for profit or whatever, interest, whatever. So here we have the same thing happening here. If you understand the example of a bank account, this is just you are opening an account in a system. Okay, just keep this in mind. So here we have energy in, again the same formula, energy out, energy generated or energy consumed, whatever. If it generated, plus sign, consumed, minus sign. For example, if you have a reaction, exothermic reaction, heat generated, you will have a plus sign. But if the reaction is endothermic, the heat is consumed. Okay, so here we have. So at point number one, now I have to write this way. See, this is a different way. At point number one, this is point number one, this is point number two. So I will write point number one, what is entering U1, KE1 plus PE, and this is the heat and the work. Okay, heat and work at point number one minus point number two. Okay, point number two, Q2, KE2, PE2, point number two. I assume there is no reaction, or I assume bank is not giving me any profit on my account and there is no consumption. Not bank, the bank is not penalizing me. Okay, so this both terms are zero. So what will I get? I assume this is zero because I assume steady state, no variation with time. So I will simply have, this is on your textbook. You can read the textbook. I think chapter number 1 or 2, it is there. So we'll have this minus this, okay, equal to 0. All right. So we know delta means 2 minus 1. U2 minus U1 is delta U. So we can write U2 minus U1 because the sign is reverse. So we have to write this way. Okay. So U1 minus U2 is delta U. Similarly, this delta KE, this delta PE, right? But there is no Q and W here, nothing. So we leave it like this one. So we take it here. We write this way, minus sign because the sign is reverse. So we write minus delta U, delta KE, PE, Q and W. Okay. We assume that kinetic energy and potential energy change. Not kinetic energy is zero because it is moving, the fluid is moving, but the change in the kinetic energy is zero. Remember this. Okay. This is wrong statement. System does not. This is wrong statement. Ignore this one. So we have minus delta U here, minus delta U, and this because we assume this is 0. So this is plus Q plus W. Plus Q plus W is equal to 0. Okay. Now this work is divided into two parts. One is a flow work and one is a shaft work. Okay, because you are pumping here. Because the fluid is flowing, there is some pumping going on. So we divide that is by the flow work. The work is coming, flow work, and one is the pump. If you have any pump here working, right, to push the liquid out or to push the gas out, you have a compressor here. Okay, in the flow system. Remember, compressor is an open system. So we put it here, flow work plus the work done by the pump. Okay, so flow work we call it PV. So we write PV as P1 V1 at the point number 1 and the flow work, pump work, and then at point number 2 the flow work is minus P2 V2. So when you take the difference P1 V1 minus P2 V2, you get delta P1. Okay, so you write here Q plus WS is equal to delta U plus PdV, delta PV. Again, you will know that U plus PV is equal to H. So we can write Q plus WS equal to delta H. This is for open system. Understand? Inshallah.
Yes, inshallah.
Okay. The only thing you need to know is this thing. When the fluid is moving, right, it is capable of doing some work. So because it is moving, we call it a flow work. Okay, this is called flow work, flow work. Another thing is that the pump, your compressor here, is moving the fluid. So you are supplying some power from here and some power from coming from here. So we divide the work in two forms. What I understand from the student, they have problem confusion here. So we have a flow work and the shaft work. This is the compressor work. So flow work is defined by P into V, pressure into volume, right? It is coming with a pressure, right? There is a pressure. It is coming with a pressure and it has a volume like the size. So when you multiply pressure into volume, you get the work, thermodynamic work. Okay. So here we have thermodynamic work. So at point number 1, P1 V1. At point number 2, minus P2 V2. So we take the difference, it becomes delta PV. Okay. So then you rearrange all the equation and this is the form of for the open system. And now you can compare. See, for open system, you have this formula, and for closed system, we have this formula. See the difference. For closed system, Q minus W delta U. Whereas for open system, we have a different formula altogether, very different formula. So here is the okay. Any question? If you have no question, then I will say I will see you next week.
Thank you, Doctor.
Okay now.